Unit 8. The D and F block elements. The D block of the periodic table consists of the elements of the groups 3 to 12 in which the d orbitals are progressively filled in each of the 4 long periods. The elements constituting the F block are those in which the 4f and 5f orbitals are progressively filled in the 2 latter long periods. These elements are formal members of group 3 from which they have been taken out to form a separate F block of the periodic table. The names transition metals and inner transition metals are often used to refer to the elements of D and F blocks respectively. There are mainly 3 series of transition metals: 3D series, Sc to Zn, 4D series, Y to CD, 5D series, La to Hg, omitting Ce to Lu. The 4th 6D series, which begins with Ac, is still incomplete. The 2 series of the inner transition metals 4F and 5X are known as lanthanoids and actinoids respectively. Strictly speaking, a transition element is defined as the one which has incompletely filled d orbital in its ground state or in any one of its oxidation states. Zinc, cadmium, and mercury of group 12 have full D10 configuration in their ground state as well as in their common oxidation states, hence are not regarded as transition metals. However, being the end members of 3 transition series, their chemistry is studied along with chemistry of the transition metals. The presence of partly filled d or f orbitals in their atoms sets the study of the transition elements and their compounds apart from that of the main group elements. However, the usual theory of valence as applicable to main group elements can also be successfully applied to transition elements. Various precious metals such as silver, gold, and platinum are industrially important metals like iron, copper, and titanium form part of the transition metals. In this unit, besides introduction, we shall first deal with the electronic configuration, occurrence, and general characteristic of the transition elements, with special emphasis on the trends in the properties of the first row 3D transition metals and the preparation and properties of some important compounds. This will be followed by considering of certain general aspects such as electronic configurations, oxidation states, and chemical reactivity of the inner transition metals. 3.1 Position in the periodic table. The D block occupies the large middle section flanked by S and P blocks in the periodic table. The very name transition given to the elements of D block is only because of their position between S and P block elements. The d orbitals of the penultimate energy level in their atoms receive electrons giving rise to the 3 rows of transition metals, that is 3D, 4D, and 5D. The 4th row of 6D is still incomplete. These series of transition elements are shown in the table 8.1. 8.2 Electronic configuration of D block elements. In general, the electronic configuration of these elements is n-1 d1 to 10 ns 1 to 2. The n-1 stands for the inner d orbitals which may have 1 to 10 electrons and outermost ns orbital may have 1 or 2 electrons. However, these generalizations have several exceptions because of very little energy difference between n-1d and ns orbitals. Furthermore, half and completely filled sets of orbitals are relatively more stable. A consequence of this factor is reflected in the electronic configurations of Cu and Cr in 3D series. Consider the case of Cr, for example, which has 3d5 4s1 instead of 3d4 4s2. The energy gap between two sets 3d and 4s of orbitals is small enough to prevent electron entering the 3d orbitals. Similarly, in case of Cu, the configuration is 3d10 4s1 and not 3d9 4s2. The electronic configurations of Zn, Cd and Hg are represented by the general formula n-1d10ns2. The orbitals in these elements are completely filled in the ground state as well as in their common oxidation states. Therefore, they are not regarded as transition metals. The d orbitals of the transition elements project to the periphery of an atom more than any other orbitals, that is s and p. Hence, they are more influenced by the surroundings as well as affecting the atoms or molecules surrounding them. In some respects, ions of a given d raised to n configuration, that n equals 1 to 9, have similar magnetic and electronic properties with partly filled d orbitals. These elements exhibit certain characteristic properties such as display of a variety of oxidation states, formation of a colored ion, and entering into complex formation with variety of ligands. The transition metals and their compounds also exhibit catalytic property and paramagnetic behavior. All these characteristics have been discussed in detail later in this unit. There are greater horizontal similarities in the properties of the transition elements in contrast to the main group elements. However, some group similarities also exist. We shall first study the general characteristics and their trends in the horizontal row, particularly 3D row, and then consider some group similarities. General properties of the transition elements D block. 8.31 Physical properties. Nearly all the transition elements display typical metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster. With the exceptions of Zn, Cd, Hg, and Mn, they have one or more typical metallic structure at normal temperature. The transition metals, with the exception of Zn, Cd, and Hg, are very much hard and have low volatility. Their melting and boiling points are high. Figure 8.1 depicts the melting points of 3D, 4D, and 5D transition metals. The high melting points of these metals are attributed to the involvement of greater number of electrons from n-1d in addition to the ns electrons in the interatomic metallic bonding. In any row, the metallic elements of these metals rise to a maximum at d5, except for anomalous values of Mn and Tc, and fall regularly as the atomic number increases. They have high enthalpies of atomization, which are shown in figure 8.2. The maxima at about the middle of each series indicate that one of the unpaired electron per d orbital is particularly favorable for strong interatomic interaction. In general, greater the number of valence electrons, stronger is the resultant bonding. Since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metal, Metals with very high enthalpy of atomization, that is, very high boiling point, tend to be noble in their reactions. Another generalization that may be drawn from figure 8.2 is that the metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is an important factor in accounting for the occurrence of much more frequent metal-metal bonding in compounds of heavy transition metals. Variations in atomic and ionic sizes of transition metal. In general, ions of the same charge in a given series show progressive decrease in radius with increase in atomic number. This is because the new electron enters a d orbital each time and the nuclear charge increases by unity. It may be recalled that the shielding effect of d electron is not that effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases, and the ionic radius decreases. The same trend is observed in the atomic radii of a given series. However, the variation within a series is quite small. An interesting point emerges when atomic sizes of one series are compared with those of corresponding elements in the other series. The curves in the figure 8.3 show an increase from the first 3D to second 4D series of elements, but the radii of the third 5D series are virtually same as those of corresponding members of the second series. This phenomena is associated with the intervention of the four orbitals which must be filled before the 5D series of the elements begin. The filling of 4f before 5d orbital results in regular decrease in atomic radii called lanthanide contraction, which essentially compensates for the expected increase in atomic size with increasing atomic number. The net result of the lanthanide contraction is that the second and third D series exhibit similar radii. Example: zirconium 160 pm, hafnium 159 pm, and have very similar physical and chemical properties, much more than that expected on basis of usual family relationship. The factor responsible for the lanthanide contraction is somewhat similar to that observed in an ordinary transition series and is attributed to similar cause, that is the imperfect shielding of one electron by another in the same set of orbitals. However, the shielding of one 4f electron by another is less than that of 1d electron by another, and as nuclear charge increases along the series, there is regular decrease in the size of entire 4f n orbitals. The decrease in metallic radius coupled with increase in atomic mass results in a general increase in density of these elements. Thus, from titanium Z equals 22 to copper Z equals 29, the significant increase in the density may be noted. 8.3.3 Ionization enthalpies. Due to an increase in nuclear charge which accompanies the filling of the inner d orbitals, there is an increase in ionization enthalpy along each series of transition elements from left to right. However, many small variations occur. Table 8.2 gives the values for the first three ionization enthalpies of the first row elements. These values show that the successive enthalpies of these elements do not increase as steeply as in the main group elements, although the first ionization enthalpy in general increases. The magnitude of the increase in the second and third ionization enthalpy for the successively elements in general is much higher. The irregular trend in the first ionization enthalpy of the 3D metals, though of little chemical significance, can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3d orbitals. So the unipositive ions have dn configurations with no 4s electrons. There is thus a reorganization energy accompanying ionization with some gains in exchange of energy as the number of electrons increases, and from that transference of s electrons into d orbitals. There is generally expected increasing trend in values as effective nuclear charge increases. However, the value of chromium is lower because of the absence of any charge in the d configuration, and the value for Zn higher because it represents an ionization from the 4s level. The lowest common oxidation state of these metals is +2. To form the M+2 ions from the gaseous atoms, the sum of first and second ionization energies is required in addition to the enthalpy of atomization for each element. The dominant term is second ionization enthalpy, which shows usually high values from Cr and Cu, where the D5 and D10 configurations of the M plus ions are disrupted, with considerably loss of energy. The value for Zn is correspondingly low, as the ionization consists of removal of an electron, which allows the production of the stable D10 configuration. The trend in third ionization enthalpies is not complicated by the 4s orbital factor and shows the greater difficulty of removing an electron from the D5 Mn2 plus and D10 Zn2 plus ions superimposed upon the general increasing order. In general, the third ionization enthalpies are quite high, and there is a marked break between the values for Mn2 plus and Fe2 plus. Also, the high values for copper, nickel and zinc indicate why it is difficult to obtain oxidation state greater than 2 for these elements. Although ionization enthalpies give some guidance concerning relative stabilities of oxidation states, this problem is very complex and not amenable to ready generalization. 8.3.4 Oxidation states. One of the notable features of a transition element is the great variety of oxidation states it may show in its compound. Table 8.3 lists the common oxidation states of the first row transition elements. The elements which give the greatest number of oxidation states occur in or near the middle of the series. Manganese, for example, exhibits all the oxidation states from +2 to +7. The lesser number of oxidation states at the extreme ends stem from either too few electrons to lose or share SCTI, or too many d electrons, hence fewer orbitals available in which to share electrons with other for higher valence CuZn. Thus, early in the series, scandium 2 is virtually unknown and titanium 4 is more stable than titanium 3 or titanium 2. At the other end, the only oxidation state of zinc in +2. No d electrons are involved. The maximum oxidation states of reasonable stability correspond in the value to the sum of s and d electrons up to manganese, followed by a rather abrupt decrease in stability of higher oxidation states, so that the typical species to follow are Fe32, CO32, Ni2, Cu12, Zn2. The variability of oxidation states, a characteristic of transition elements, arises out of incomplete filling of d orbitals in such a way that their oxidation states differ from each other by unity. Example: vanadium 2, vanadium 3, vanadium 4, vanadium 5. This is in contrast with the variability of oxidation states of non-transition elements, where oxidation states normally differ by a unit of 2. An interesting feature in the variability of oxidation states of the d-block elements is noticed among the groups 4 through 10. Although in the p-block the lower oxidation states are favored by heavier number due to inert pair effect, the opposite is true in the groups of d-block. For example, in group 6, MO6 and W6 are found to be more stable than Cr6. Thus, Cr6 in the form of dichromate in acidic medium is a strong oxidizing agent, whereas MoO3 and WO3 are not. Low oxidation states are found when a complex compound has ligands capable of pi acceptor character in addition to the sigma bonding. For example, NiCO4 and FeCO5. The oxidation state of nickel and iron is 0. The table 8.4 consists the thermochemical parameters related to the transformation of the solid metal ions to M2 plus ions in solution and their standard electrode potentials. The observed value of E0 and those calculated using data of table 8.4 are compared in figure 8.4. The unique behavior of Cu having positive E0 accounts for its inability to liberate H2 from acids. Only oxidizing acids, nitric acid and hot sulfuric concentrated react with Cu, the acids being reduced. The high energy to transform CuS to Cu2 plus aqueous is not balanced by its hydration enthalpy. The general trend towards less negative E0 values across the series is related to the general increase in the sum of first and second ionization enthalpy. It is interesting to note that the value of E0 for Mn, Ni and Zn are more negative than expected from the trend. The stability of the half-filled d subshell in Mn2 plus and the completely filled D10 configuration in Zn2 are related to their E0 values, whereas E0 for Ni is related to the highest negative delta H hydration. Trends in M3 M2 standard electrode potentials. An examination of E0, M3 M2 values shows that the variation trends. The low value for scandium reflects the stability of scandium 3 which has noble gas configuration. The highest value for Zn is due to removal of an electron from the stable D10 configuration of Zn2 The comparatively high value for Mn shows that the Mn2 D5 is particularly stable, whereas comparatively low value for Fe shows the extra stability of Fe3 D5. The comparatively low value for vanadium is related to the stability of vanadium 2 half-filled T2G level. 8.3.7 Trends in stability of higher oxidation states. Table 8.5 shows the stable halides of the 3D series of transition metals. The highest oxidation numbers are achieved in TiX4 tetrahalides, VF5 and CrF6. The +7 state for Mn is not represented in simple halides, but MnO3F is known. In B and Mn, no metal has trihalide except FeX3 and COF3. The ability of fluorine to stabilize the highest oxidation state is due to either higher lattice energy, as in case of COF3, or higher bond enthalpy terms for the higher covalent compounds. Example VF5 and CRF6. Although V5 is represented only by VF5 and other halides, however, undergo hydrolysis to give oxohalides VOX3. Another feature of chlorides is their instability in low oxidation states. Example VX2, where X equals chlorine, bromine, or iodine. And the same applies to COX. On the other hand, all CO2 halides are known except the iodine. In this case, CO2 plus oxidizes Y minus to I2. However, many copper 2 compounds are unstable in aqueous solution and undergo disproportionation. The stability of Cu2 plus aqueous rather than Cu plus aqueous is due to the much more negative delta H hydration of Cu2 plus aqueous than Cu plus, which more than compensates for the second ionization enthalpy of Cu. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. The highest oxidation states in the oxides, table 8.6, coincides with the group number and is attained in Sc2O3 and Mn2O7. Beyond group 7, no higher oxides of Fe above Fe2O3 are known, although ferrates are formed in the alkaline media, but the readily decompose Fe2O3 and O2 minus. Besides the oxide, oxocations stabilize V5 as VO2 plus, V4 as VO2 plus, and titanium 4 as TiO2 plus. The ability of the oxygen to stabilize these high oxidation states exceeds that of fluorine. Thus, the highest Mn fluoride is Mn4 plus, whereas the highest oxide is Mn2O7. The ability of the oxygen to form multiple bonds to metals explain its superiority. In the covalent oxide Mn2O7, each Mn is tetrahedrally surrounded by O's including MnO, Mn bridge. The tetrahedral MO ions known for V5, chromium 6, Mn5, Mn6 and Mn7. Chemical reactivity and E0 values. Transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve in mineral acids. Although a few are noble, that is, they are unaffected by these simple acids. The metals of the first series, with the exception of copper, are relatively more reactive and are oxidized by 1 molar H+, though the actual rate at which these metals react with oxidizing agents like hydrogen ion H+, is sometimes slow. For example, titanium, vanadium in practice are passive to dilute non-oxidizing acids at room temperature. The E0 values for M2 plus M indicate a decreasing tendency to form divalent cations across the series. The general trend towards less negative E0 values is related to increase in some of the first and second ionization enthalpies. It is interesting to note that the E0 values for Mn, Ni and Zr are more negative than that expected from the general trend, whereas the stabilities of the half-filled D subshell D5 in Mn2 plus and completely filled D subshell D10 and zinc are related to their E0 values. For nickel, E0 value is related to the highest negative enthalpy of hydration. An examination of E0 values for the redox couple M3 plus M2 plus shows that Mn3 plus and CO3 plus ions are strongest oxidizing agents in aqueous solutions. The ions Ti2 plus, V2 plus and Cr2 plus are strong reducing agents and will liberate hydrogen from a dilute acid. 8.3.9 Magnetic properties. When a magnetic field is applied to substances, mainly two types of magnetic behavior are observed: diamagnetism and paramagnetism. Diamagnetic substances are repelled by the applied field, while paramagnetic substances are attracted. Substances which are attracted very strongly are said to be ferromagnetic. In fact, ferromagnetism is an extreme form of paramagnetism. Many of the transition metal ions are paramagnetic. Paramagnetism arises from the presence of unpaired electrons, each such electron having a magnetic moment associated with its spin angular momentum and orbital angular momentum. For the compounds of first series of transition metals, the contribution of the angular momentum is effectively quenched and hence is of no significance. For these, the magnetic moment is determined by number of unpaired electrons and is calculated by using the spin-only formula mu equals root n into n plus 2, where n is number of unpaired electrons, mu is the magnetic moment in unit of Bohr magneton. A single unpaired electron has magnetic moment of 1.73 Bohr magneton. The magnetic moment increases with increasing number of unpaired electrons. Thus, the observed magnetic moment gives a useful indication about the number of unpaired electrons present in the atom, molecule, or ion. The magnetic moments are calculated from the spin-only formula, and those derived experimentally for some ions for the first row transition elements are given in table 8.7. 8.3.10 Formation of colored ions. When an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. This frequency generally lies in the visible region. The color observed corresponds to the complementary color of the light absorbed. The frequency of the light absorbed is determined by the nature of the ligand. In aqueous solutions where water molecules are the ligands, the colors of the ions absorbed are listed in the table 8.8. A few colored solutions of d-block elements are illustrated in the figure 8.5.